Okay, so we have now Niels Warburton from the University College Dublin with the main seminar, Gravitational Waves from Small Radio Binaries. So go ahead when you're ready, Niels, and thank you for participating.
Great, thanks. Is the shared screen visible?
Yes,
Yeah.
thank you.
Great, that's perfect. Thanks a lot. Okay, yes, so today I'm going to talk about small mass ratio binaries and how those are modeled just within GR. And yeah, just to introduce myself, I currently work at University College Dublin, and there I'm a Royal Society Science Foundation Ireland University Research Fellow. So first of all, let me just say thank you very much for the invitation. I really wish I could be in Mexico for many reasons. I miss the people there, and the food is amazing. I live in Ireland. It's hard to get such flavoursome food. And I've been a few times, and the last time was in 2005, where myself and Cesar, who was giving a talk later today, enjoyed a great many taco al pastor in Coyoacán. So although I can't be with you at the moment, I hope I can in future years. So for my talk today, I want to talk, as I said, about gravitational waves and small mass ratio binaries. I'll split this into roughly 4 sections. First of all, a little bit of motivation. Why are we interested in small mass ratio binaries? And that will come in a combination of current gravitational wave observations. So most of those have been for quite comparable mass ratio binaries, but we're starting to see systems with more distinct mass ratios in them. There's also recent exciting results showing the existence of intermediate mass black holes. So I'll touch on those. And then I'll also talk about things called extreme mass ratio inspirals, which is where we have a massive black hole and a small compact object. And that's been the main focus of my research during my career. But recently, there seems to be applicability to other problems. I'll then discuss the status of modeling black hole binaries in general, with a focus on how do we actually model these small mass ratio systems. And then I'll talk about using black hole perturbation theory, which turns out to be the most appropriate way to model such systems, and in particular, an extension of black hole perturbation theory beyond the normal linear order that you might be used to. So if you've ever done any black hole perturbation theory, you might have looked at the Reggie-Wheeler equation or the Tucholsky equation. These were derived back in the 60s and 70s. And that was linear perturbation theory. And we've, a huge amount of work has come out of that, but now we're pushing beyond that to nonlinear black hole perturbation theory. And so I'll just sketch out the framework for that. It's reasonably complicated. I won't give too many details. And then for the latter, let's say about a third of the talk, I'll talk about some new results that we've recently produced by our group here in University College Dublin, as well with collaborators at the University of Southampton. And that will then shed some light on, at least in terms of perturbation theory, what actually counts as small, i.e. how far can we push perturbation theory into modeling quite a wide range of mass ratios. So as I said, I would start by a bit of motivation. So why are we interested in small mass ratio binaries? And I thought I'd start by this nice plot that came out recently after the release of the first or second O3 catalog from the LIGO-Virgo collaboration, which shows all of the black holes and compact objects, or many of them that we know in the universe now. And so what this is showing is here the mass of the components and a variety of different systems. So in yellow are shown the neutron stars that we know about electromagnetically. In orange, we know neutron stars we know about from LIGO-Virgo observations. In purple, we see the electromagnetically known black holes, generally X-ray binaries, so from accreting black holes that are known for accreting matter. And then in blue, we see the LIGO-Virgo black holes that have been observed. Now, these tend to be heavier mass, probably a selection bias here because binaries with larger components disturb the spacetime more, so they're easier to detect from a larger distance. And we see that they're kind of, a lot of them are in the kind of range 20 to 30 solar masses, merging to something between 40 to 60 or even 80 solar masses. And so there's been a huge burst in these detections recently. It's been, I think we've heard people say already, we're kind of in a second golden age for black hole science, and I think I agree. But I want to draw your attention to 2 particular systems on this diagram. The first is this system here, which, if you can see, has the merger of some small or very light object, most probably a black hole, but could be a very heavy neutron star. It's not completely clear. And that's merging with an object which has a black hole, which has something like 20, 22, 23 solar masses. And so if you look at that system, that has a mass ratio of 1 to 9. So that's the most extreme system that we've seen so far in the data that at least has been released. And an interesting question is, is for the least for the purposes of perturbation theory, is that going to be a small mass ratio binary? Could we model something like that with perturbation theory? We'll come to an answer to that towards the end. The other system I wanted to highlight is this one here, the heaviest system. So this was formed from two black holes merging something like 60 and 80, 85 solar masses or so into a remnant of about 150 solar masses. The signal is pretty short, but as long as you believe it's a quasi-circular binary rather than something else, then you would assume this system is now the first detected intermediate mass black hole, which are generally taken to be black holes with more than 100 solar masses. And these are very interesting objects. They're actually very hard to detect electromagnetically. And so it's interesting we have a first confirmation that such things exist. Of course, once you can create such a black hole, you can then create binaries with such black holes. And those are also interesting. So with this confirmation of intermediate black holes exist, this of course raises the possibility of what are known as intermediate mass ratio inspirals, or IMRIs. And these are binaries where the mass ratio is in the range of 100 to 10,000 to 1. And so here I'm showing a simulation that was made by a colleague of ours, Steve Drasko. This is showing a 2,000 to 1 mass ratio binary. And this simulation is shown in real time. So if you were able to see the system, obviously you wouldn't see this trail, but you would see this black hole and this small dot going around it. And this is how you would actually see it moving at a substantial fraction of the speed of light. And the time scale here is set by this. The primary here is 3,000 solar masses, and the secondary has the mass of a neutron star. And you can just see from this simulation that the orbital period is something like a second or so, maybe slightly slower. And so this isn't the kind of thing you could measure with a ground-based detector, which tends to struggle due to seismic noise below sort of 10 hertz. Future detectors might get down to 1 hertz. So for these sorts of systems, you're typically talking about building space-stage detectors. In particular, you might be looking for a decihertz detector ideally suited to intermediate mass ratio inspirals, or indeed a millihertz detector such as the LISA spacecraft. These are certainly very interesting systems, and there's a great deal that's unknown about whether or not these things exist, and if they do, where they live. Do they live in dense stellar clusters? Can they form binaries? Can we get these sorts of inspirals? And as usual with gravitational waves, in order to find them, we have to actually have this a theoretical template, a waveform model in advance in order to pluck those signals out of the data. So there's another good reason to model these small mass ratio binaries. The main reason that has dominated my career, though, is looking at even more extreme systems. So where you have a massive black hole, as we know to exist in the center of most galaxies, and that then has an inspiral with a compact object, right? So we know that massive black holes exist in dense stellar clusters. We expect them from time to time to capture in orbit some compact object, either a neutron star or a black hole. And when it does, it will form a system with a mass ratio around 10 to the 5 or 10 to the 7 or so. These are known as extreme mass ratio inspirals. And then the orbital period is of the order of tens of minutes or hours, and the frequency then is in millihertz. And that makes it ideally placed to be a candidate to one of the key sources for the laser interferometer space antenna, ESA, is future space-based gravitational wave detector. And so here I'm just showing the strain that you would expect for the LISA detector, along with some of the key sources. We have the massive black holes, which are very loud in the LISA detector. We have some of these stellar origin black holes. These are the things that go on to merge in the LIGO-Virgo band. And then at the bottom here of the bucket, these tracks here show the harmonics, in this case, of an extreme mass ratio inspiral. So I will focus most of my talk. I'll talk about MRIs, but keep in mind I'm talking potentially about intermediate mass ratio systems once we have the ability to detect those, and maybe even more comparable mass systems, and I'll get to that as I go along. So let's just flesh out a little more about these extreme mass ratio inspirals and set a little notation. So I'm going to have a massive black hole, or a larger black hole, let's say, of mass m1. So the primary has mass m1 and are orbited by a secondary of mass m2. In principle, these two things could be spinning, and there's no particular reason to believe that the spin would be aligned in any way for most formation mechanisms you'd expect for these systems. I won't say too much about spin in this talk, but I will mention it on a couple of slides. What I'm going to do is define the mass ratio epsilon to be what we call the small mass ratio. So it's the smaller mass divided by the bigger mass. And so this is a number which is much less than 1. As I said before, we typically think the primary of being a massive black hole, just thinking GR here, and the secondary is some compact object, such as a neutron star or a stellar mass black hole. And we require it to be compact because otherwise it's going to be tidally disrupted before it gets into the deep, strong field of the massive black hole, which is where it would emit the kind of strength of gravitational waves needed for detection by LISA. So the typical mass ratio range for these systems is sort of 10 to the minus 4 to 10 to the minus 7. The key features of them is that they are, as I said, millihertz ground gravitational waves sources. They will, unlike LIGO sources, which typically have detected maybe at most a few thousand cycles for the binary neutron star, these will have hundreds of thousands of cycles in the strong field, all detectable by the detector. This means that the signal is present in the LISA band for months or even years. It wouldn't be unexpected to have an emery that would actually last the entire duration of the LISA mission, which is something like 6 years before any extension. And as I said, they're very generic. There's no spin alignment expected. They can have considerable eccentricity, unlike currently detected sources. So eccentricity is up to 0.7 or 8 as they enter the band. And this leads to a very rich waveform phenomenology, but also challenges with modeling. And so as you've seen before in that little animation, the typical motion of, in this case, the geodesic motion, which would look like a snapshot of the emery, is very complicated of the secondary around the primary. But these signals have very low instantaneous signal to noise ratio in the detector. And so the only way we can actually pluck them out of the data is to have very accurate waveform models that can be convolved with the data stream in order to see if that particular signal is present. So that's motivation for modeling these systems. Okay, so that's a little bit of motivation about why we want to look at small mass ratio binaries. I think there's lots of interesting science you can do with them. The question is, how do we solve, in general, the two-body problem in a general relativistic context? And so I'm sure many of you've seen this, but I will just go over it quickly. So generally, we think of the different methods, and here I'm showing 3 of them. There are perhaps a couple more, but these are the key ones I wish to talk about. And we think of them as their applicability is whether they model binaries that are close or widely separated, and also the mass ratio of the binary. So if we want to model systems that are widely separated, we can use what is the oldest theory, but basically started to be developed by Einstein, which is sort of perturb around the Newtonian solution and perform ever higher expansions. In this case, it empowers some small parameter, which is some velocity associated with the body divided by the speed of light. And so long as the binary is widely separated, this will be the case, and you can accurately model the system. But this will break down in the strong field, and it cannot be used anywhere near merger because this series expansion doesn't converge well there. And in fact, it's only known up to a certain order at the moment, about 3.5 to 4 post-Newtonian order, depending on whether you're looking at the dissipative or conservative sectors. When you are deep in the strong field and your masses are comparable, then people turn to numerical relativity. So here we solve the full nonlinear partial differential equations of Einstein's theory on supercomputers. It took a huge amount of work just to even get those equations to solve stably, but now this is routine, and since 2005 we've been able to do that. But this, although it can give you the correct solution, it is extremely expensive. I'll mention that in a moment, and this actually restricts substantially the parameter space that these simulations can cover. In particular, they can't start the binaries too far apart because then it would just take too many cycles for it to actually merge all the way down to plunge, and we just don't have the computing power or the patience. And likewise, we also can't start with a particularly small mass ratio, because for 2 reasons: you need to have extra resolution to resolve the smaller body, and that then limits the Courant limit, and means you have to take extra time steps in your simulation. And furthermore, as the mass ratio gets smaller, you get more cycles. So as I said, with LIGO Virgo sources, you might have 40, 50, 60 cycles in the detector, but if you need to model 100,000 cycles, this is not the kind of thing you'll be able to do with numerical relativity. And so finally, in this region where you're both in the strong field, but you have a small mass ratio, we turn to perturbation theory, or black hole perturbation theory, and also some aspect of it called the self-force, which I'll mention. And on this diagram, I haven't really given any sense of scale, so I haven't said where the line is between these two things, and this is actually a blurred line, of course, but hopefully by the end of this, I'll get a little closer to answering how far you can push perturbation theory to modeling more closer to mass systems. So for the small mass ratio systems, we're not going to use these two, we're going to use black hole perturbation theory. Also, just one more thing to say about the numerical relativity, about how far those are able to do and what sort of mass ratios they are able to cover at the moment. Since its inception in 2005, there's been a lot of simulations, and now people run simulation catalogs of results that are available out there. There's a few of these. Georgia Tech has one, RIT, BAM, it's public. But one of the most well known is this Simulating Extreme Spacetimes catalog. It's a publicly available catalog from simulations done using the spec code. Back in 2003, that catalog contained 174 binary black hole simulations in this piece of the parameter space. Here on the z-axis, it's showing the mass ratio Q, which is 1 over epsilon. It's their preferred mass ratio. We don't need to worry too much about the spins here, but if you look along this axis, you can see that they have a bunch of non-spinning systems all the way out to mass ratios of 8, so 1 to 8. Now, most recently in 2009, they released a new catalog now with 2,000 binary black hole simulations. But again, you can see the mass ratio coverage is all the way up now to 10, so it hasn't extended much further than the mass ratio, that they have obviously added many more simulations inside the parameter space up to there. If you take one of these simulations, in fact, this one here at the end, basically, and you plot it, then this is what you get. You see you have something like 40 cycles. And this, the key thing to point out, particularly in comparison later, is that this took months, many months, on many hundreds of cores of a supercomputer to compute this waveform. And actually going beyond, you might have heard there are a few simulations going a bit beyond 1 to 10, 1 to 15, or 1 to 100 in very special cases. But in general, it's extremely hard at the moment for numerical relativity to go much more 1 to 10, and certainly 1 to 20. Okay, so now let's talk about black hole perturbation theory, which is going to be the main topic of the talk. So what we're going to do is we have a new small parameter because of the small mass ratio. We use epsilon equal to m2 over m1. And we're going to use that to expand the metric of the binary around the generally analytically known metric of the primary. So here, the reminder is the system we're looking to solve for. We want to compute the gravitational radiation coming off. And we will do this by expanding the metric of binary G around some background metric, which will be G bar, which will generally be the Schwarzschild or Kerr metric, plus some first order correction, a second order correction, and potentially higher order corrections, as long as you have strength to continue the calculation, or perhaps more importantly, grant money and PhDs and postdocs to help you. In these models, it turns out to be sufficient to model the secondary as just a point particle, so a delta function moving along the world line. You can add extra multiple moments if you want to look at spinning bodies, and I'll mention that towards the end. But for now, this is how we'll model the secondary. At least on these scales, we don't care about the internal dynamics of the secondary. So if it's a neutron star, it's not particularly important that it's different from a black hole. And then the name of the game is to take this expansion, substitute it into the Einstein equations, and then solve order by order. So it sounds easy enough, but of course, the devil is in the details. And the equations of motion of this secondary around the primary, it's a leading order would be geodesic motion, but then once you start including back reaction from these metric perturbation terms, then you start finding a forcing term appears on the right-hand side of the geodesic equation, which we refer to as the self-force. So I'll explain what that is now. So here's our setup. We have our massive black hole and our secondary going around it. And if we're considering the secondary to be a test body, then we know well that this follows the geodesic of the background spacetime. But as soon as we give this finite mass and it induces a perturbation over the metric of the primary, that perturbation will scatter off the curvature of the spacetime set up by the primary. And this allows it, some of it, of course, will escape to infinity, that's the gravitational waves, but some of it will then re-interact with the smaller body at a later time. And that can happen just by scattering off the curvature, also by the distortion of the light cones around the black hole. And so you can get, propagation going around the black hole and re-interacting with the particle at the secondary at a later time. And when this happens, then we like to think of this results in a change in the trajectory of the particle, and we say that's due to a force that's come about, and that force is because of the metric perturbation of the body itself, and that's why we call it a self-force. So this self-force depends upon the local metric perturbation, which is of course a function of the entire past history of the particle which has set up that perturbation. If you like to think about light cones, then we can think of the force at some field point x separated away from the world line z, and that force is computed from perturbations that have traveled both along the light cone and also within the light cone, because we have a curved spacetime. This is something that doesn't happen in the flat spacetime case, where we don't have support here from perturbations that have traveled along the light cone, but because we're in curved spacetime, we have support as well on the interior of the light cone. Now here this is fine, but as we've set things up with a point particle, if you actually now take the limit of this field point goes to the world line, which which corresponds to calculating the force at the body itself at some later time, you'll find this diverges, and there's a need then to regularize the equations. So I won't talk about the regularization in depth, only to say that it is extremely rigorously and well defined. So I'm going to start talking about subtracting singular pieces from the calculation. I won't give any more detail other than just to say that this is a well-defined process. And it can be defined rigorously through what's called matched asymptotic expansions. So we can treat we have an outer expansion where we treat the field of M1 as the background, and that's then perturbed by the presence of the smaller body. So you have a tidally perturbed M1. We can also just zoom in around the small body, and we can treat the smaller body again as a swash-ordered curved black hole, which is then tidally perturbed by the presence of the bigger black hole. And there's some buffer region in between the two, and by ensuring consistency across that region, we can define this regular singular split, basically. As I said, I won't say too much about this, but if you are interested in the details of how this is done, there's a bunch of papers here that go through it in gory detail. There's a nice review paper here, and then some extra papers of the second order perturbations that I'll talk about. And I'll make these slides available afterward if anyone is interested. Basically, though, what it boils down to is that our retarded metric perturbation, which I'll call HRET, can be thought of, it's defined because we've chosen a point particle model. It has a singularity on the world line, but it can be thought of as being made up of a singular piece, which contains all that singular behavior, plus some smooth regular piece. And then it turns out, and what this matched asymptotic expansion derives and shows, is that the self force is actually computed only from the derivatives of this regular metric perturbation on the world line. So the key thing to understand here is just that this split exists and it can be done in an unambiguous, rigorous way. And one final comment is that this singular field here, it's not normally globally defined, it's just locally defined near the body in some normal neighborhood, basically. And so we typically refer to this, rather than a singular piece, as what we call a puncture field. And so I'll often talk about HP being puncture field, which is the approximation to the singular behavior near the body. Okay, so before we actually go and actually look at the expansion by putting things in the field equations and expanding and looking at the equations we want to solve, a key question whenever you're doing any perturbative expansion in any area of physics is how high in that expansion do I actually need to go in order to capture the physics I'm interested in, right? At some point you might want to stop calculating Feynman diagrams because you've calculated all the things you care about, even though in principle you could go higher. So here it turns out that we want to go to second order in the mass ratio expansion. And why do we know that? Well, we learn this by looking at the phase of the waveform, which is the key thing we care about for gravitational wave science. We need to accurately track the phase in our models in order to pluck out the signals in the data from the detectors. This has a contribution which scales as epsilon to the -1, and a contribution that scales as epsilon to the 0. And then once we get to contribution that scales as order epsilon, well, we don't care about these anymore because epsilon is 10 to the -6 or 2. We expect this to be very small and not be too important. So this leading piece, this piece that scales as epsilon to -1, is known as the adiabatic piece of the waveform phase. And mercifully, this is easily calculated, or more easily calculated, from the fluxes of the gravitational waves, which you can compute. Again, if you've ever done a Tucholsky or Reggie-Wheeler calculation, you can compute from the asymptotic boundaries of the perturbation. And then you can use a balance law to work out the force that actually appears on the body that drives the inspiral. And so we've been able to do well now since 2005 for generic orbits in Kerr spacetime. And if you have just access to this, then this is generally good enough for the detection of very bright sources, so very loud, high SNR signals. And this might be good for those to do a little bit of astrophysics with MRIs, but really emphasis here that only true for the bright sources. And so you'll be losing a lot of potential observations. So that comes from the leading order metric perturbation and the fluxes. What appears at this what's known as the post-adiabatic order, well, there's some things that oscillate on the orbital timescale, which are part of the self force that you can't get access to from the flux because these are orbit averaged. And there's also a piece in the second order metric perturbation. So it's crucial to have that in order to get your waveform accurate to this level with a residual of order epsilon. So you need this to extract all the sources you have in your data stream. So there may be many hopefully tens or more, hundreds or thousands of active MRIs in the data. You may have also heard that MRIs can be used for precision tests of GR, probably the most precise sources we expect to be out there. So there's a lot of talk at this conference about testing GR and testing alternative theories. MRIs would be a great way to do that because you're talking about measurements of the order of 10 to the minus 3 or 4 relative precision in various parameters of the system. And then finally, there's also a potential application to these intermediate mass ratio systems that I'll talk about as we go through the talk. Okay, so we know we need to go up to second order. That's what we need to do. So let's see what the field equations look like. And again, I'm just going to sketch things here without getting into the gory details. So we're going to take our expansion. We have our background metric, Schwarzschild occur, our first order metric perturbation, and a second order metric perturbation. We'll shove that into the Einstein operator and expand out order by order. So what do we get at zeroth order? Well, we know that the background metric is a vacuum solution, so nothing unexpected there. More interesting, of course, is once we move to first order. So now we have this G1, this is the linearized Einstein operator, acting on the first order metric perturbation. And this is sourced then by the normal source. So the secret is there's a factor of epsilon hidden in here that would have appeared on the previous slide. And so a lot of work to do now. Then I'll mention some results, but the main focus of this talk is what happens when you go to the next order. So when you go to the next order, because the Einstein operator is nonlinear, we get two contributions. We get the linear Einstein operator acting on the second order metric perturbation, and we get this G2, this second order operator, which is made up of products of the first order metric perturbation. And so these now are the equations we want to solve in order to compute the motion of the body. So these, as I said, these are the linearized Einstein operators. Just in order to the notation here, I'm going to drop the ones and I'm going to drop the alpha betas everywhere to stop carrying that around. And I'll just replace this linearized operator with the box because it's leading behavior. Certainly once you pick a suitable gauge, has the usual behavior of the box operator, the wave operator. So this is now the equations that we care about solving, and let's look a little bit about how we actually do this in practice. So the first thing we can note is at second order, we can move this term here, the second term, onto the right-hand side to make it a source for our second order perturbation. So we go ahead and do that. And so now we have an equation that we like. Our box operator is now sourced by some combination of first order metric perturbation terms. Right, so the second order perturbation is sourced by the first order metric perturbation. Now, unfortunately, it turns out that this thing is ill-defined. It doesn't make any sense. It has products, effectively products of delta functions in it, and it's horrendously divergent. And so how do we proceed? Well, remember I talked about we have to regularize these equations in order to make them make sense. We have to split the retarded contributions, which are these H1 and H2, into a regular and singular piece. So we can do that. We can split these into a regular piece. In this case, as I said, we'll call it a puncture piece. We'll do the same at second order. And then because this is a linear operator, by linearity, I can expand this out, and I can move box of H2P in particular onto the right-hand side here. So I'll do that. And so now I'm solving for this regular piece. Remember, it's the thing I need to actually compute this self force that will drive the inspiral. And this turns out that when appropriately defined, this quantity on the right-hand side is now well-defined and regular, and you can work with this. So what are these different terms? So remember this T, this is the usual point particle source. This is the usual box operator. The real crux of these calculations that I said before is identifying what is this puncture field. And that was done at second order only recently, or reasonably recently, in 2012, two papers that came out that year by Adam Pound and Sam Gralla. There are additional challenges at second order that don't exist at first order. This T is just has support on the world line, and this puncture can actually, at least at first order, can also be made to just have support on the world line, or at least it's compact. But at second order, remember the second order perturbation is sourced by the entire first order metric perturbation. And so this term here is both non-compact, so it's non-zero everywhere in the space-time, and it diverges at the particle, although that divergence is cancelled by this term here. But that subtraction is difficult, at least numerically. But let's suppose you can compute these two things. Once you have it, then your equations of motion here, again, just a slightly different form, the geodesic equation plus some first order forcing term and a second order forcing term. I'm blowing over huge amounts of detail at this point, but just to say that there's some extra challenges that come from the fact that we only know this puncture field in a very particular gauge, known as the Lorentz gauge, given by this condition. So the divergence of the trace reverse metric perturbation must be zero. And even worse, these equations then still cannot be solved in the Lorentz gauge because we actually have never been able to do that for the PDE form, even at first order. So we have to look to something else. So this is, again, just some of the gory details quickly. What we do is we move into the frequency domain, and we do this using a 2 timescale expansion. We have to do this because the secondary is actually inspiraling. And we can define what we call a slow time, a t tilde, equal to epsilon, the mass ratio times t, and a fast time. So these 2 times, so slow time is basically the radiation reaction timescale, and the fast time is the fast orbital timescale given by phi p, which is the azimuthal angle of the particle. Using that, we can expand out our time derivative operators in the previous PDEs, and this basically expands the box operator to have a first order, a 0th order piece, and an extra term order proportional to epsilon. This is just a long way of saying these then are the final equations we want to solve. These operators here, these linearized Einstein operators get expanded once more. We can move one of those terms onto the right-hand side, and then this becomes the source we actually have to solve for. Actually doing this is tricky. We've had to develop effective source techniques in the frequency domain. So this term here is referred to as an effective source. There are issues, again, special problems on large length scales. There are challenges actually constructing this object, particularly near the world line. If you want to see some more gory details, there's a nice talk at the Capra meeting that I provide a link to here. And this work now has been ongoing since I finished my PhD and back in about 2012, 2013, in fact, and we've been slowly publishing a lot of papers that go through the details here. And then just in the last few months, we've got the first results that I want to present to you next. I should just very briefly say, of course, there had lots of very exciting results at first order in the mass ratio. We first understood what this puncture field was back in 1997. And since then, about 20 years until, actually pretty much 20 years until 2017, when Martin van der Ment published results for the first order cell force along a fully generic orbit in Kerr spacetime. That's when the secondary is not spinning. We do actually care about the case when the secondary is spinning. It influences the flux in an important way. But there's recent papers that one I've been involved with and another group from Rome studied to calculate this as well, but for more simple orbital configurations. Of course, here I'm just talking about computing the metric perturbation and computing the force. Once you actually have that, you have to then drive the inspiral and then actually compute waveforms. And there's been a lot of work that myself and others have been involved with. So here's a few snapshots of kind of computing the inspiral of a body going from a highly eccentric inspiral. Slowly you can see it shedding eccentricity and becoming more circular before it eventually plunges. And then, of course, the key thing of gravitational wave science is we actually need to pair the signal that we get from the detectors with hundreds of millions of waveform templates. And so we need to compute these waveforms very rapidly. And then just as a bit of advertisement, we have a recent piece of work a few months ago now showing how you can actually compute hundreds of thousands of cycles using a combination of neural network and GPU techniques. So if you're curious, have a look there. So we can now compute these things rapidly, at least at first order in the mass ratio. Okay, so for the remainder of my talk, I want to talk about, I've just given a sketch to the calculation. You could easily give a whole lecture series on this calculation, but we'll stop there. I just want to talk about the results that we're getting at second order in the mass ratio. So basically solving this equation. And so the main challenge comes from actually computing this source here on the right-hand side. And so to make things easy, or easier at least, we will start with just the simplest orbital configuration. We'll talk about quasi-circular inspirals into a non-rotating Schwarzschild black hole. And then within the 2 timescale expanded version of this equation that I mentioned, we can go ahead and actually compute the gravitational flux that we get through to second order in the mass ratio. And then that's what I'm going to talk about for the remainder of the talk. One of the things I'm going to be really interested in is basically this question of how far can you push perturbation theory to cover a wide range of mass ratios. In order to do that, it makes sense to switch from expand everything at one of these other mass ratios that you can define. So far we've been using epsilon, which is equal to the mass of the secondary divided by mass of the primary. We'll also introduce Q, which is favored by numerical relativity researchers, which is 1 over epsilon, so mass of the primary divided by mass of the secondary, so it's always bigger than 1. And there's also a kind of more physically motivated mass ratio called the symmetric mass ratio, which we'll call nu, because it doesn't matter, if you change the labels on the binary, it shouldn't change any physics. You just call this one M1 and this one M2 and then switch them. And that's precisely what the symmetric mass ratio does. This is given by the product divided by the square of the sum. So this M here is the total mass of the binary. You can write this in terms of Q this way if you like. We're also going to parameterize the orbits. Instead of using the orbital radius, which is a bit gauge dependent, we'll use something related to the orbital frequency. So this omega is the orbital frequency, and capital M here is the total mass raised to the 2/3 power. You can roughly, if you like, think of x as being 1 over the radius of the body. But then using these definitions, we can rewrite this flux that we'll compute from our perturbation theory calculation. So we can go ahead and compute all the metric perturbation, and then we can evaluate it asymptotically. And from that, we can then compute the radiated gravitational wave fluxes. In the actual calculation, we compute it as a function of R naught and epsilon. But just using these relations, we can re-expand without losing information and write it as a function of x, this separation parameter, which is favored by Pn, and the symmetric mass ratio. And there's some relation between them. That's not too important, but it can be done. So this leading term here is what we call the first order term. It scales as nu squared. And this second order term scales as nu cubed. So there's a global factor of nu that pulls out. So the very first thing we want to do, these calculations are very complicated. It's taken us a number of years to do that. And so what we want to do is compare our perturbation theory result to other ways of solving the two-body problem. And so we'll start by looking at comparisons with post-Newtonian theory. So for the purpose of this talk, I'm going to look at the L equals 3, M equals 1 mode. So rather than the 2-2 mode, that's because it turns out our data in the 2-2 mode is not yet. It could be better, basically. There's still some noise in that data, but for the 3-1, it seems to be very nice. And so you can go ahead and look in the literature. So Fay et al. Have computed the contribution to the gravitational wave flux for the 3-1 mode, which is given here. And of course, PN series do not give any, they give you everything to all orders in the mass ratio. So here's a first order term, here's a second order term, but here at order x to the 7th, we have a third order in the mass ratio term, which we're not able to calculate at the moment. And we want to explicitly compare against second order in the mass ratio pieces. That's the terms that are order nu cubed. So here is the beginning of the PN series. I've just truncated it to fit on the slide. And we can extract these terms of order nu cubed, and I can write them all down. And this actually shown here in the middle is the entire known PN series. So after 100 years of calculation, this is the amount of analytic knowledge we have for the flux in the 3-1 mode. This is everything that we currently know. So what can we do? We can go ahead and compute our flux from our perturbation theory and compare that with post-Newtonian. So here I'm showing that. So here these dots are the output of our numerical relativity, our black hole perturbation theory second order in the mass ratio calculation. And we're just computing the second order flux and comparing this as a function of the orbital separation. Over here, this is the weak field. So you expect results to agree most with PN over here. This is the strong field. As I said, you can think of x as being roughly 1 over the radius. So here there's actually 1 over 5. So it's beyond the kind of test body ISCO in a most stable circular orbit. And out here, it's more like 1 over 20. So 1 over 50. So these dots show our numerical data, and this blue line then shows the leading order post-Newtonian term, which I've highlighted here, 6 x to the 6th divided by 315. And what you can do then is go, well, that's nice, they seem to agree, and they should certainly agree over here. We expect some disagreement in the strong field because PN isn't very good there, but they should agree as you move into the weak field. So I can now subtract our data from the analytic prediction and hopefully find something subdominant underneath. You can go ahead and do that. And indeed, when I subtract the blue dots from the blue curve, I get the yellow dots. And then I can repeat this game. So now I've got the yellow dots, which is showing the difference between our result and the leading PN result. I can then subtract off the next 2 terms. It turns out to be useful to think about the next 2 terms. I've plotted that here as the yellow line. I can subtract those 2 again. We're starting to see, again, nice agreement. It starts to break down here because there's some noise in our numerical data, but that's okay. I can do this once more. I can subtract the PN from the numerical results. And again, you still see agreement. Again, it's breaking down here, but it looks like things are behaving. And this is it. This is as far as you can go with analytic PN knowledge. You can't do any more subtractions, but we can still subtract this this red curve from the red data. And this gives you an estimate for the currently unknown 4PN term. And so you can see it seems to fall along a line at x to the 19 over 2, which is where you expect the next term to be. And you can estimate the coefficient there of being roughly this size. So you can actually use this to extract higher order PN terms at order nu cubed in the PN expansion. Okay, so that was nice, and that was basically a check on our results. But what we've been really interested in is a comparison with numerical relativity. And so that's what I'm going to show, and this is going to kind of then answer that question: what is a small mass ratio binary? How far can you push this perturbation theory approach? So for this comparison, which really just happened in the last couple of months, it's useful to consider the flux normalized by the leading post-Newtonian term. So here, for example, is the 2-2 flux for the PN series. This is the famous 32 over 5 nu cubed x cubed, the quadrupole term. And then here's the subdominant terms. And I'm going to define an f hat just to be the normal flux divided by the leading PN term. So this normalizes the first term of that series just to be 1. And then this is the rest of the expansion. There are more terms known, I just haven't shown them here. In order to compute the numerical relativity flux, we get the waveforms, in this case from the SXX catalog, and we can split those up into an amplitude times by a complex phase. And then from these two pieces, we can compute the flux as a function of time from the time derivative of the waveform, and we can also compute the separation from the phase, basically, from the time derivative of that. And combining these two, we can then compute the flux as a function of the separation of the binary. Okay, so here I'm going to plot those results for the various different approximations and see how well they compare with what you consider the correct result, which is the case modulo numerical noise from numerical relativity. So here I'm plotting on the right, this is this f hat, I've been explicit, this is the flux divided by the 0 PN term, the leading quadrupole piece. And here again is the separation, this x parameter, and over here is the weak field where PN should be good, and here is the strong field, and here in this the test body limit is where the innermost stable circular orbit lies. And I'll plot the flux for the 2-2 mode and for Q of 10, so mass ratio of 1 to 10, or 10 to 1, which corresponds to the symmetric mass ratio of 0.08. So you can plot the post-Newtonian result here. This is up to the 3.5 PN, the highest order that is known currently. And then if I go ahead and plot the numerical relativity result, then you get this blue curve here. You can see some small oscillations, there's some noise appearing in the simulation. You can see it doesn't go very far into the weak field. In fact, there's actually a gap between the PN result and the numerical relativity result. But you can believe that this sort of connects up to here if they were able to run the simulation for longer. The next thing I will plot is the first order result. So what we get from first order perturbation theory, which I've called 1 GSF, or gravitational self-force. And actually this is the result that you could have plotted, the same curve, you could have plotted this in the 70s. So once people have written down the Reggie-Wheeler-Tucholsky equations and solved those for circular orbits, you could have made this curve. But now, as of a few months ago, we've now extended that and actually made the first nonlinear calculation in black hole perturbation theory. And this gives you the second order in the mass ratio result, which is now this red curve. And what you can see rather nicely is that this now agrees quite well with post-Newtonian in the weak field. So remember, post-Newtonian contains all orders in the mass ratio, but really interestingly, also seems to agree really well with the numerical relativity simulation in the strong field. So again, obviously that's the full correct answer. So our result here at second order mass ratio is excluding higher order terms, but you see it doesn't seem to matter very much, even at a mass ratio of 10 to 1. We're getting nice agreement through much here deep into the strong field. Now there is, in the end, some disagreement as you start to approach the innermost stable circular orbit in the very strong field. And there's two reasons why that might be. One, in our calculation, we're assuming a quasi-circular inspiral, and that starts to break down as you get close to the ISCO. There's a transition to plunging and the merger. So something about our approximation is breaking down. Or possibly, of course, higher order the mass ratio terms might be becoming important. We've not yet done enough analysis to work out what that is, but nonetheless, we're still very excited to see such good agreement. And just as a reminder, this numerical relativity simulation would have taken months to compute. Just this single mass ratio here, once we've computed our calculation, we can run this, compute these plots in milliseconds, and we get almost exactly the same curve over at least quite a wide portion of the separation space here. Okay, so that's been very nice. We see that things are looking good at Q10. How about we do something completely outrageous and we look at Q1. Now remember we're doing an expansion in the powers of the mass ratio. And there's no reason to think that my small mass ratio expansion will work where the expansion parameter has a value of 1. So let's just, why not? Let's do it and see how it goes. So here is now the same plot, but now the binaries, the two components of the binary have exactly the same size. Nu takes a value of 0.25. Again, you can see the first order result is not very good. That's the green curve. But our second order result, there is now a small discrepancy, but agrees surprisingly well with the numerical relativity result. So the two black holes are the same size, modeled with black hole perturbation theory. And you can see how close the red curve is to the numerical relativity data. So we really wouldn't expect it to work here at all, but even there, it does seem to do surprisingly well. Okay, so this is just for the 2-2 mode, the dominant mode. What about maybe some of the higher modes? So here we go back to Q10. We see that actually the second order result doesn't seem to work quite so well. So this is now for Q10 and the L equals 4, M equals 4 mode. So a higher mode. So it contributes less to the total waveform, but the agreement with second order perturbation theory doesn't seem as good. But you might notice that what's interesting is it has the right sort of shape. It's just off by a constant offset. So can we understand, first of all, why is this agreement not so good? And maybe we can sort of correct it in some way. So why does this second order flux not compare very well against numerical relativity for the 4-4 mode? Well, if you look at the leading post-Newtonian term for the 4-4 mode, it contains a first order correction from nu squared, a second order correction nu cubed, but also a third order correction that we don't have access to from our perturbative calculation. And compare this with the PN series for the 2-2 mode. So here in the 2-2 mode, the third leading term, the subleading, the sub-subleading, only once you get to the term of order x to the 7th, so quite deep into the series, do you see the first term that appears, which has a nu to the 4th, the third order in the mass ratio term. So can we do anything about this? Well, we can try what's a simple resummation. So we can try to include some data that we know from the PN series, combining it with our cell force data. We can do it the following way. We can write our cell force result like this. We can divide out by the PN term. We can then re-expand this and multiply by this term. And this then ensures that in the weak field, this f hat, which is the term normalized by the leading term, goes as 1 plus. So basically this re-expansion forces the behavior to be correct in the weak field limit. And if we do that and return to our plot and do the simple resummation, we see that we get some nice results. Now we agree in the weak field as the resummation has forced us to do, but we also then agree quite nicely even in the strong field. And you can see we have very nice agreement with numerical relativity between our second order results and numerical relativity results. And I should emphasize here, I don't think I said it, we haven't got error bars on this NR result. They're probably of the order of the oscillations you can see on the plot. And we actually don't yet have error bars on our own result. So I'm not quite sure what the error bars are here. And that's because these results are really very fresh. We got them about 2 months ago. And since then, I actually had to be lecturing for the last 2 months. So that's kind of slowed down the research. Okay, so getting close to rounding up, we can look at this more quantitatively. We can see what is the error between numerical relativity and our second order perturbation theory results. And we see we typically have an error, again, without error bars, but a difference in our data of about 0.1%. This starts to grow larger when you don't do that resummation, but once you resum, again, you see it's about 0.1%. These points here in the strong field, we can ignore because we're probably breaking down our approximation. And the same is true for, in this case, the 4-4 mode. So we do see that the pure second order result does worsen for high L modes. And this suggests that the comparison might not be as good for orbits with lots of power in those higher modes, when this can include really strong field orbits around Kerr. Remember, we're just using a Schwarzschild black hole as our background, or highly eccentric orbits. But these modes do contribute less to the total flux. And so it's the most important thing is what the behavior of the 2-2 mode is. Because as we know, it's the dominant mode in gravitational waves. Let me just conclude.
Sorry, you have 10 minutes left.
Great, thank you very much. That's perfect. Let me conclude just saying a little about what happens if the secondary is spinning. So in the calculation I presented for the second order, the mass ratio calculation, we've assumed the primary is a Schwarzschild black hole. That makes our life easier. We have more symmetry, it's spherically symmetric. And it's going to be quite a lot of work actually to change this to being a Kerr black hole. We've started on that, but I would say the first results are probably 2 to 3 years away. And one of the reasons for this is we have to move away from this Lorentz gauge where we understand things quite well because it's no longer separable in Kerr spacetime, so we can no longer decompose this into modes and do our usual tricks. But nonetheless, we can model the spin on the secondary quite easily within the pole-dipole approximation. So here I'll define, again, the mass ratio, but we can also find the sigma as a measure of the black hole or the secondary spin. And if you think of this secondary as being a black hole, you can think of the sigma as varying between 0 and 1. So it's like the Kerr spin parameter. And so for self-force calculations, the most relevant cases where these two things are comparable, and the compact secondary is a black hole neutron star. And then we have an expansion that looks like this. We have a first order correction, but also a first order with spin correction as well. In order to make these calculations, very similar again to what we did before, we have the stress energy, which is a delta function within the world line, but now the spinning correction, we have a derivative of a delta function, where this S that appears here is now the spin tensor. And then, as the usual, when you have spinning secondaries, you have to pick a spin supplementary condition, like decide where the center of mass is. And it turns out to be useful to linearize in the spin. We don't need higher order terms in sigma. Once you do, then your self-forced equations of motion get modified. You have the usual self-force plus some term that couples to the background spacetime through the spin tensor. So these are the usual Matheson, Papa-Petz, and Dixon equations of motion. And you also get a term which we call the self-torque, which can spin up or spin down or change the angle of precession of the secondary. And so we've recently solved these equations. Others have done as well as before, but we look quite carefully at the balance law and the local force in this paper here. And also computed the flux, crucially. So what can we do with that? Well, we can then go ahead and compare our results again to numerical relativity. So here's another example. Same thing again, we're plotting the flux normalized by the leading post-Newtonian behavior. We're plotting as a function of the orbital separation. So here again, the weak field, and here the strong field. And this time I'm plotting a binary with a mass ratio of 6.3. So that's a nu of 0.11 or so. And here the secondary, the primary is non-spinning, or pretty close to being non-spinning, about 10 to the minus 2. This chi is the effective spin, or the spin parameter, measuring the spin of the binary. But the secondary is spinning at minus 0.8. That's its Kerr spin parameter, or dimensionless Kerr spin parameter. And so this blue this blue curve here, the wiggly one, that's the numerical relativity result. There's some initial transient, and then we see that. And if we just compare against our self-force result with no spin at second order again, we see they don't agree very well, and perhaps that's to be expected. But we now add in the spin calculation. So we just take the results from that paper and literally just add the two numbers together, the two fluxes. We get this red curve that appears. And now you see, once again, even though our secondary is spinning quite rapidly, we have really nice agreement through much of the strong field, again, breaking down in the deep strong field, but with the numerical relativity results. And so this, again, quite a high mass ratio, Q1 6.3. And we really didn't expect it to work so well there at all. Normally you think of perturbation theory being for these extreme mass ratio systems, a mass ratio 10 to minus 6 or so, maybe 10 to minus 5, 4 is good, but it seems actually quite good even up to 10 to the minus 1 or 1 over that for Q. Okay, then, so just to summarize, I started at the beginning by saying, we do expect in the future to observe many more of these small mass ratio binaries, typically about 1 to 10, maybe 1 to 15 is the kind of thing you might be able to see with LIGO detectors. You're not going to see much more because you need a big primary and a small secondary. And as the primary gets bigger, the total mass of the system gets higher and the frequency drops out of the ground-based detector range. As always, we need good waveform models for these binaries. And as I talked about, we need to use perturbation theory in order to do that. And we know from MREs you need to go to second order, but what's most interesting recently from these new results is it actually looks like perturbation theory can actually model binaries all the way up to mass ratios of 1 to 10, which is really quite spectacular. And with the caveat, of course, at least when the primary is not spinning, it's going to take a while to check that, and when the orbit is circular, which is still limited. And of course, here I've just talked about the flux. We haven't yet computed the waveform. That will come in the next few months, and then we'll make the final comparisons. And I'd like to emphasize, that those waveforms, when we compute them, we'll be able to compute them in a very rapid timescale in comparison to the numerical relativity waveforms. So I'm not suggesting for a moment this replaces numerical relativity, but at mass ratios 1 to 100, when numerical relativity is always going to really struggle, this is almost definitely the way to go. So I think I'll finish there. Thank you very much.
Thank you very much, Niels. Very nice talk. So we have time for a couple of questions, comments.
Yeah.
Now,
Can you hear me? Yeah. I wasn't able to raise the hand, but anyway. Hey, Niels, how are you doing?
Good, how you say so.
So yeah, I was about to ask just the last thing you said. Like all your curves just apparently match kind of perfectly those from numerical relativity. And in terms of observation, I mean, these higher modes are actually relevant, or those may not be seen in generations of detectors.
You mean modes beyond the 2-2 mode?
Yes.
Yeah, those are definitely very relevant. And so in that system, the first one I introduced and said they had this 1 to 9, that was the first binary where I think they had unambiguous detection of the higher modes. So it does matter that indeed, we have this discrepancy in, for instance, the 4-4 mode. Now, this is a mass ratio of 1 to 10, which is really abusing perturbation theory. At 1 to 100, where we actually have no numerical relativity simulation to compare against, you would expect these to agree very well. And so certainly I think for intermediate systems and beyond, this is the way to go. And I think you'll still get useful information for the kind of ground-based detectors that you can use basically in building your waveform models.
So in which systems would it be really, really bad? So say detectable ones.
With current detectors?
Yes.
Yeah, well, like I said, I think with current detectors, you're not going to see systems with much more than about the 1 to 10, maybe 1 to 15 of what they're seeing. It probably gets worse as well if the system was not quasi-circular. So far, all the binaries we've detected are quasi-circular. Once you move to eccentric binaries, you start putting more power into the higher modes. And that means that the higher modes, the 3-3, the 4-4, the 2-1, and so on, start to become more important. And so it's likely that our results wouldn't work so well for those systems. Now, again, I emphasize we don't expect perturbation theory to really work so well as it seems to. But yeah, for those systems, it would be the worst. But for the quasi-circular systems we do see, I actually think this can probably add and say useful things for some of the current waveform models.
Great, thank you.
Thanks.
thank you, Cesar. Thank you, Niels. There is one question in the chat. So Christian Peterson, do you want to ask? Or I can read it for you.
Yeah, no, I can ask. Sorry.
Okay.
Yes.
Okay.
Hello. I'm just curious about the state of the art of the second order gravitational self force, including spin. But if you have, my question is, if you have to calculate second order self torque and all that stuff you presented in the last slide.
Yep, that's a great question. So at least, let me see, what's the best thing to see? So here, so because this sigma and epsilon, sigma is of the order of epsilon, this is already competing with this second order term. So still a first order term, but if you're only going to this distance in the expansion, that's all you care about. And you can compute this completely separately. This is a thing you can compute at first, and it's nowhere near as challenging as a second order calculation. Of course, you could try and compute second order corrections, including the spin. They would then appear and compete with the third order corrections. And so no one has attempted that yet because we haven't given any thought yet to doing third order because it's very difficult. So in terms of spins on the secondary, it's not necessary to go any further because although you might be able to do it, you don't have the other piece that contributes to the same order. And so without the two pieces, you haven't got the whole picture, and it's only complete when you do. It's worth saying perhaps at second order in the phasing, I mentioned at the beginning, let's keep going here. So this is the post-adiabatic term. These terms here, these oscillatory terms that appear at first order mass ratio, we've known about these for quite some time, since 2007. But the new results in the really nice agreement with numerical relativity only comes about when you include everything that appears at this order, including the second order calculation. So it's important to include everything at the same order and then make your comparisons.
Okay, thank you.
Okay, thank you again, Niels.
Thank you very much.
So our next speaker is